Welcome back to Ninibus. Um, I hope the journey till now in the bus not as bumpy as we thought of, right? We are going very slow and trying to derive all the requirement, the trade-offs, the design decision slowly and steadily, right? We are not going to be hurry going forward also. Everything should be derived from the first principle. Okay, that is the basic philosophy around the Ninibus, right? This lecture is going to be fun because we are going to uh, do something new. Okay, I will not say it's out of box, but it's not the traditional thing what we did till now, right? So till now, what we did is like we have a lane ID, we have a single producer, and producer put the data to the lane, and one consumer will come or read the data. And if we have multiple consumer or multiple subscriber for that same lane ID, now every subscriber or every consumer have to fight for each other. All right, I am telling it's going to be fight for each other. Once one consumer read their data, it's going to be deleted from the queue. All right, because we are storing the data in the queue. All right, so when the next consumer come, for him or for it, we don't have the data, right? It going to read the next available data. That means the current consumer is missing, right? Missing some data, and this is became a competitiveness between the subscriber or between the consumer, right? So one consumer read the data is gone. Okay, so now they have to fight, right? Whoever comes first, he will get the data, right? And that's a good behavior in some of the use cases. We will have that behavior we require, right? Maybe we have multiple consumer, but they don't want the same data, right? Hmm. You can think of worker queues, right? It's kind of a worker queue, right? You have multiple consumers or worker, and in the queue some tasks are available. You take the data. That means for that part, for that particular data, what is read by one worker, it's done, right? We don't have to do anything. The next worker should come and it's going to read the second available data, right? That's the correct behavior, and it is also an required behavior, right? So if you want to use the Ninibus, and if you have this requirement, right, then you can use this last v1.0 dot 0 v1 not 0. Okay, sorry. Okay, so that can be used for your application, okay, for your use case. But be keep in mind, we are not have implemented the multiple threads, right? Everything's are part of a single thread. Okay, that's the implementation was not yet done, and we don't know when we are going to implement those scenarios also. Yeah, we are going definitely going on the direction slowly and evolving also. We are going to implement, but at this moment it's not implemented. So if you have a single thread, and in a single thread um, uh, you want to read the data with multiple consumer, you can do it. Or if you have some external synchronization at this moment, you can also use this one. Okay, saying all those background stories, this session or this lecture, we are going to introduce one new concept or a new problem statement, or we are going to increase the Ninibus scope little bit more. The reason the problem statement or the or the scope what we are increasing and we are going to solve so slowly, if we have a single lane, one producer putting the data, but we have now multiple consumers, and every consumer wants to read all the data, right? No one wants to skip anything, right? So in a queue, so one writer or one producer putting the data. Okay, I am not going to implement multi-producer, okay, or I am not going to implement multi-producer putting the data in the same lane ID. No, the lane ID abstraction was done because I want the producer, every new producer or every unique producer should put their data in a different lane ID. Okay, I don't want to have a single lane ID for multiple producer. No, the idea was behind that need to be concrete, so that every lane ID means there's every it's a unique producer. Okay, so that part is not required. So now the second part is come, but on a single lane ID we can have multiple consumer, okay, or subscriber, and they want the data, right? Now this is something we are going to develop. Okay, now in this video we are not going into the code, but definitely we are going to derive something, which are definitely going to make some architecture decision today, and the code will follow. So let's reiterate the problem statement again. So every consumer will have his cursor ID, okay, his index, that I am reading now. The current position is 5. I am reading from the queue position 5. Let subscriber 1 reading queue position 5, subscriber 2 reading queue position 8. Okay, so okay, next time one subscriber 1 come, it will read 6 and subscriber 2 reads 9, right? Because once one subscriber read, it will increase its own cursor or on index, and the previous or the next subscriber will increase its own cursor. Okay, that's fine, but the problem is that now we cannot delete the data. Once I read it, I don't know is there any other consumer or subscriber is there who is behind me, so he may need that data what I read, what this first consumer or first subscriber read. So delete is not possible. Okay, we will discuss how we can delete and all those things. We have to make some policy how to delete. Okay, that's clear, right? This part is clear, that a single queue can have multiple subscriber. Okay, now what we have implemented in Nini cfifo, which is a queue kind of data structure, right? That's not going to work out, because in queue once you read the data is gone, but that cannot be used here, right? We need something which can store the data up to some extent. Okay, so definitely the queue doesn't going to fit here, so we need to have a new kind of data structure, a new kind of implementation required. Okay, so let's do some thing around it. Okay, so what we discussed is that every subscriber will have his own cursor ID, right? So once I'm telling, hey, I am subscriber ID 1 or 2, I want to read the data, I should have a lookup table. I can find, okay, subscriber ID to current read sequence is 20. So the next read sequence will be 21. So I need a lookup table, right? Some lookup table which will help me to get the cursor ID of the subscriber, right? So saying that, the first thing what we need is one subscriber ID and its own cursor, right? So I need a lookup table. So why not a map? So map is a good data structure. Let's use that one. Okay. So I need a map. So let use something called unordered map. Okay. So here I need a subscriber ID. Okay. Let define a subscriber ID, right? Something subscriber ID type. Okay. Some variable like UN32 or 64, anything. And what else is needed? I need one more thing called sequence. Okay, the index where I'm reading or writing to. Sorry, I'm reading, not writing. No one subscriber doesn't have the power to mutate. Okay, because it cannot delete. It cannot mutate. It only read only, right? So it will read. So I need something called a read sequence. So let sequence ID. Okay, so I have this two data structure, like I have this map now. So looks fine. Now what else? After this, so let this map name I will give something called cursors. Cursor means I'm just trying to tell for me cursor is something like cursor is something like that, the index, the read index. Okay, that is the cursor for each subscriber. And in this map I am storing all the cursors, current cursor of all my subscribers. So that's why I given the name as cursor. Okay, what else I need? I need a storage buffer, right? Why am I storing the data? I need a buffer. So let's use some vector. Okay, some vector. Okay, I need some buffer. Okay, we know that we are going to implement bounded buffer, right? Because we don't have all the memory in the world. So we need a bounded buffer. That means my vector should not go beyond certain limit memory size, right? So let the capacity, it have a capacity variable, right? So let it have a size, something called size type, which may be in 32 or 64, whatever we want to implement. So it have a capacity variable. So your queue should not grow beyond capacity, right? Okay, that is the bounded. So once it reaches to the capacity, let you have defined my capacity is 5 or 100 or 1024 1 KB, right? Once you reach that capacity, now you need to reclaim, right? Reclaim the slots. Okay, slots are the index of buffer. Okay, so okay, one more variable I need, right? Size. What is the current size? I have a capacity that I can write 124 slots. I am not going to tell it's a bytes, okay, because my buffer data type is not yet defined, so it can be string, right? But buffer size is capacity, right? A buffer have a 124 slots. How many capacity I'm giving? I'm thinking virtually I have that many only slots available to me, right? And I need a size variable which will tell me I have a 124 but I have used only 10, so my size is 10, right? That's how typical a data structure or STL works, right? The size definitely tell you how much you have used till now, right? So I may need a size. Okay, nice. So So when I'm telling it's a bounded, right, that means once I reach to the end, I need to go back to the start, right? I need to go back to the start. Okay, so if you know the ring buffer kind of thing, right, what it have, it have a head, it have a tail, right? Tail is something which is telling me what mean, it's a ring, a queue, right? Ring buffer is a queue. So you should read from head and you should push the data into the tail, right? So I need two more variables to be managed, right? So I can tell those variables are head sequence and tail sequence. Head sequence is here is the head now, here is the tail now, the tail sequence. So let I have something called sequence type head sequence and something I need for tail sequence, right? And that we have those data types, right? And sequence type, size type. In the code you can see what we have defined, but for the moment making it easy to understand, right? I'm just putting it. Yes. So these two things we require. That's good discussion. I don't think I need any data, any variables now, right? Nice. So what operations is going to do? Two operations mostly, right? Someone can read, someone can write. That's all, right? Nothing else. So I need something like read result. So once you read, I will return you back something, right? Read. So when I'm going to return you back something, I'm telling you, if you remember, we have implemented something called backpressure. To handle backpressure, I've given you how many slots are till need to be consumed, or how many pending messages are there in the queue, but you have not reached there, right? That is the read result will tell you, right? And the second part will tell what is the state of the queue, what is the read result, right? It is the okay, it's not okay, the lane not exist, you don't have a cursor for it, okay? So that's a read result. It will be going to be little bit a structure kind of thing. Do not argue at this moment why to return a structure. Okay, we can do something else, but we are not going to optimize anything yet. The optimization will come later. The first thing is make it concrete. Things should work fast. Then we will see the needs and beats where we can do something optimization that we will do later. Okay, so we are going to read. How we are going to read? You have to tell me what is your subscriber ID, right? So that I can go and look my lookup table and check, okay, the current read recursion is here, so read it, increment my cursor, right? So I need your subscriber ID. So I need a subscriber ID here, right? Okay, then I'm going to write, read and write. It is the two fundamental thing I'm doing, right? So write result. So write result again, you know, right? Write result again, you are going to tell buddy how many slots are still available for you to write, right? Have you reached the capacity? If yes, slow down, don't write. You need to handle the back pressure. But you see you have 50 slots available to be written. That means you can write quickly. That's how it's defined, right? So the write result will tell you something called credit. If you remember lane credit, every lane will tell you how much credit. So the write will essentially going to tell you how much credits you have which can be written. Okay, so I have to pass you two things, right? I have to pass you. What I have to pass you? I don't know pass because for this data structure I don't need any cursor. I know anything you're going to write, I'm going to write on the tail only, not on the head, right? I don't need anything. So just write. So give me the message. Okay, one thing I missed here. Read result will return you back the status, pending messages. But where your data is? Like what you read? That is the main thing, right? So I want user to pass his buffer. I don't going to use my buffer. I want to pass user to be passed this buffer. Okay, now read and write is done. What else? What else? This part is done, I hope. Okay, now I need to do few more things, right, which is not going to be visible to the user, but I need to do it. Why I need to do it? The reason being, once my queue is full, I reach to the capacity, my tail is reached to the head now, like it's a ring buffer, right? How do I manage? How do, when I'm going to free one slot so that I can start writing, otherwise the queue will be full, no one going to write because I cannot delete when read, right? So I need some policy to free it, right? So that is up on me, so I can make it a private variable, right? I don't need anyone to know this, so I let just come something called the claim slot. I don't know how I'm going to define it, how I'm going to implement it, but I know I need it. Okay, these things are fine. Now before I going more about this programs and APIs, I want to discuss one really good thing, really good thing. There are two things I want to tell you. One is your virtual thing. Okay, two things I want to be. So let me tell you something called virtual sequence, and I will tell something else called physical index. I will tell you what these two things and why I am doing this one. We'll do it together, no problem. So think of this. So this is my buffer, right? And I have a capacity which is 4. That means I have only 4 sides. So 0, 1, 2 and 3, right? That's my capacity. Okay, so at the starting my head will be at this position, and my tail also having to this position. Nice. So what the tail means the next slot where I'm going to write, right? So if the queue is empty, tail is potential at 0. That means it's telling you write. If you're trying to write, I will write on the tail 0 or sequence 0. Okay, then once I write it, I will move the tail to 1, right? I will move the tail to 1. So the next time you write, I will write into 1, then I will move the tail to 2. Then I reach to 2, you write to 2, and I will move the tail to 3. Or next time you write to tail, I will write to tail. Okay, 0 already 10, right? So I will move the tail to here, right? I will move the tail to here. Now I can see here I cannot write to tail anymore because I don't know this I should reclaim or not. Okay, think of that. There is some way I reclaimed it. There is some policy I made that once I tail reach to the end, I will reclaim it. So now my tail will be 0 and my head also move, right? Because now it's not the current head, right? Because in the ring buffer, like the head is the oldest data, right? So the oldest data is here, so my head will be moving to this position, my tail goes to 0. Interesting. So now think of what happened. These are 0, 1, 2, 3 are my physical index, right? My physical index. Now my physical index again 0. So now I will write again my physical index of 1 and 2, like this will go 0, 1, 2, 3. And what is the virtual sequence? And why I reached to this point, let me tell you something. Think of this way. This is a queue. Okay, this is a queue of size. I'm just increasing the size to make it a little bit better. I am making the size to 6 or 7. Okay, so the index is 0, 1, 2, these are slots 4 and 5. Okay, so now you have a subscriber which is okay. Now think your tail is at the end. Now tail is here. Okay, you already reached to the last, but that means you reach to the last, but this is empty till now. So your last data is here, 4 is here, and I move the tail to here. So next time I write a tail, I should write to here. Let's think you have a subscriber ID 1. You have a subscriber ID 1. His cursor is at index 2. That means next time when you're going to read, he'll read from 2, and once he read 2, he'll move to 3. So if you know, I always going to tell that what is your pending messages, how many messages are pending for you to read, right? That is Backpressure I'm trying to handle, and it's a unique thing I'm trying to implement, right? So now my cursor is at 2. My cursor is at 2. I do a read operation. So my cursor reaches to here. My cursor reaches to here through 3. So how do I calculate the pending message? How many pending messages are there? So I read 2. So from I have these 2 messages are 3, right? So my pending message is my current tail minus the cursor. So when I'm reading it, I will read from the current cursor. I will read from the current cursor, like my message should be like my buffer current cursor. Okay, read the data. Once I read it, the message is full. So I was at 2, so I read the data from 2. The cursor will always tell what the next data I am going to read, right? So I reach to 3 now. Okay, so for you now, 3 and 4, these two are available data, right? So my tail is here, right? So I have to increment my current cursor, and I have to tell pending goes to my tail and my cursor. Nice, all looks good. Now let one write happen. So write happen to 5, and my current cursor is at 3, right? This is here, this is here, this is here, and I return a tail. Okay, now how is the next tail will go? It will 0. It will reach to 0, right? It will reach to 0. And don't think how it reach to 0, because I am not deleting anything, so it should not go here. Think of once the queue is full, my policy is that I will delete it for a moment. Think it. So I reach to 0. So now the current cursor come, this person came and try to read one value. So it will do, my current cursor is at 3, so it will read the data of 3. Okay, data is at 3. Now my current cursor plus is to 4. Okay, so now I have to calculate pending message. How many messages are pending? So pending messages are 4. Okay, this is pending message, this is a pending message, this is a pending message. So the pending message are 3 actually, because I have written this index also, right? And my I have written this index, and my tail is here, right? I have written this index, so I have 1, 2, 3. So if I put this formula now, tail at index 1 and my current cursor is at index 4, I am getting minus 3. 1, 2, 3, but I should get 3 actually, right? I should get 3 actually. Now you can tell that I can take an absolute value. Yeah, you can take, and then you will feel later point something else also required. This only absolute value may not work, because you are dealing with multiple cursors, right? Yeah, so then there's some mathematical things are required. Okay, and for that I have this is maybe derived. So for that, let's thought of a solution. Okay, here I am trying to something called a read sequence instead of, and I have something called index. Index are the physical index. Okay, so and I have a write sequence. Write sequence are nothing but tail sequence, right? Where the last thing I'm writing. So I have a tail sequence. These three things. So now I have a buffer. Okay, of size 4. Once I reach to tail, my tail is at 3. The next I'm going to write, I'll write to here, right? I know I'm going to write here. Instead of I make it to 0, but if I can make it to 4, let's increment. So my tail sequence will be 4. But from 4, I can calculate the index. That's easy, right? What I can do a tail sequence modular capacity, which will be my tail index. Okay, that means 4 is okay. Now if my read sequence is at this point, right, like 0 1 2 3, right, read sequence is this condition, read sequence. So now I can tell from 4 minus 2 is 2. That means you have 2 data only, right, for pending messages. That looks beautiful. Now it looks fine because I have 2 data only. So now again one write happened, I reached to here, my tail sequence became 5. My tail sequence became 5 and my physical became 1, right? So the 4 became 0. Okay, so my current index is here, which is reading sequence, right? So I reach to here. Okay, so my size will be again 5 minus 3, which is 2. 5, my total index, my current cursor is 3, so 5 minus 3 is 2, and that's correct, right? Because I have only these 2 data which is not read it. Looks fine. Now let my read sequence or my cursor read this one and reach to this point. Okay, okay. So and my tail sequence is here. Okay, and let it read this sequence and I reach to here. Okay, what's happening now? So shall I make it to 0 read sequence? No. Again the calculation will be a big problem, because if it is you are making this one is 5 absolute value and become 0, which is absolutely wrong. It is giving you 5, but for you have only this data, only 1, your pending message only 1. So instead of moving or wrapping around the read sequence, let's read sequence we go sequentially, and that's fine, right? That's a good thing in this case. And what does it physically means is that it means that how many bytes or how many slots are written till this point and how many data you have read till this point. I don't know the physical index. I don't want the person, the producer or consumer, they don't need to know how I'm managing the queue, but they should know how many slots I've written. How many slots means how many times I've given write, and the read is will get I have reading this sequence, so I can calculate, I can give you the skipped messages, that this many messages are skipped or pending, sorry, not skipped, it's pending. So I have written I don't know about the queue, but the writer written to into something, some index, some sequence 1000, and the reader may be 800, right? So they don't deal about how I'm handling the queues wrapping around, but they have absolute value. Every time they put, their sequence is increasing. Every time they read, their read sequence is increasing, right? So they don't have to worry about how I am doing it. So they are getting the absolute value, right? Okay, I have written 1000 slots. I have written 500 slots, 800, 900. Read, I am reading 200, 300. Okay. Sorry. Looks simple, right? That's beautiful thing, right? So we have countered, right? We have make something read sequence and write sequence. So that's why the sequence can go like 0 1 2 3 4 something tick 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 tick, and my index will be always 0 will be 0, 1 will be 1. Once I reach to 4 it becomes 0 because by my index is sequence modulo the capacity. Okay, I can calculate the index from the sequence. I don't need to store the index, right? I can calculate from there. Looks like one caveat here. One caveat. The sequence, what type of variable will do? U int 8. After 255, what will happen? It will become 0. Oh my god. Back to the same problem. Back to the same problem. U int 16. Maybe after a few more time, back to the same problem. U int 32. It will be back to the same problem after some time. Increase it, U int 64. Yeah, back to the same problem. Huh? No, 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 no. Think up, think up. If you write data every 1 second, sorry, if you are writing data in every 1 microsecond, okay, every 1 microsecond you are writing a data, and with the size of 2 in 64, 2 power 64 minus 1, do a calculation. If I am writing it every 1 microsecond, how much time it will consume to do the wrapping around? Think up, think up. 1 microsecond, every 1 microsecond writing 1 message, right? So my counter will be, my sequence will be plus plus. That means 10 power 6, 10 power 6 times I will write in every second, right? In every second 10 power 6. So my sequence will be like 10 power 6. It's 2 power 64, it's 10 power 6. Okay. Now think up in every minute into 60. Every minute, every hour, another 60. Okay. So it's like 3600 into 10 power 6, which will become 36 into 10 power 8. Am I correct? Yeah. Okay. 3. This is in a day, in a R. In an R I am writing this is in an R. So this will be a sequence number, right? So in a day, so 24 into 36 into 10 power 8, 24 hours in a day, right? So this is a day, so 24. Okay, so what is 24 into 36? So make some nearest thing. 24 into 36 is like how much? Think of 25 into 25, 620. Like put it 1000. Okay, put it 1000. This is approximately 1000. So 10 power 3. So 10 power 8, which is become 10 power 11. Not bad, not bad. In a month, in a day, I'm writing 10 power 11. In a month or in a year, 360 power into 10 power 11. I am making 365 like, okay. So this I can write 365 into 10 power 365. I'm making around 4, okay, 400. I'm making around 400 into 10 power 11. So that means 2 power 2 into 100, which is 10 power 2 into 10 power 11. So which will be like, I don't know how much time it will take to come. So this will be like 2 power 2, so 4 into 10 power 13. Okay. In a year. So you think we have a 2 power, so in a year the sequence will reach to here. So you will think how much time it will reach to wrap around. So 10 power 3, let it make it little bit, okay. Let me put it 10 power 3, 10, I let make some nearest around 16, making the upper limit. So let's make it 16 power 13, so which will be like So like, which it means 2 power 4. So 2 power 64 into 4 is 2 power 2. 10 I'm making 16, right? Or 2. I'm just trying to make it calculation like 2 power 4 into 13, right? Plus 13. So 2 power 64, and if you write 2 power 17, 2 power 19. So you think. So this is a year. This is for a year. So how many years it will take? Okay, the calculation looks like a little bit wrong to me. If you do properly, it will come something around 567,000 years to wrap around that value. So if someone is using my implementation, and if they started today and after around 567,000 years it became wrap around, it's an issue, it will class, it will give an undefined behavior. But I will think, or I will ask them to appreciate us because we survived 5 lakhs years, 567, okay, 5 lakh, 67,000 years. It will definitely going to class. It will class on that day. It will not class. It will have an undefined behavior. Okay. Okay, that's what I want to tell. Okay. Why we have a read sequence and write sequence, right? What else is required? We read and write. One more thing we didn't forget: reclaim. When you are going to reclaim the memory, otherwise, if you once you reach to the queue's end, or you become size equals to capacity, you have written to the last slot, and you don't know where is your last reading cursor, who is the slowest reading, so that I have this one. Okay, I reach to this point now. I written. Okay, I read to 10, and I don't know my so let I have multiple cursor. I have a cursor here. I can have a cursor here. So when I write the next data, where to write? You think if I have this is one cursor, this is one cursor. That means this is my slowest cursor, right? So that means slowest means that is the last cursor, like very slow cursor, is reading very slowly. So that means every data from here is red. So what I can do is I can claim the head. To the slowest cursor. One caveat. If my slowest cursor is at this point, not read anything, what I will do? I can stop. So I am trying to do a trade-off or a design philosophy. I'm trying to put one design trade-off. I am going to reclaim my memory when my queue is full. When I am writing, I will reclaim. If my queue is full, I will find the slowest cursor. I will delete you. I will remove you from you. And that means if I remove you, this is the second slowest cursor. That means my tail can come to here actually. My tail can come to here. Okay. If this is my big queue somewhere, and one cursor is here, one cursor is here, the slowest cursor is this one, the second slowest cursor is this one. And what I will do? I will delete you from memory. Yeah, man, you go. I don't want you because you're the slowest one. I have given you enough hint. When you are reading, I have given you enough hint that you are slow. You handle back pressure. Even the writer also I told that I have small memory, big memory, right? I have telling how many slots are available. So I have given you enough information, but you didn't do anything. But you are still slowest. I will delete you, man. Okay, I will delete it from you. If I delete it, then how I can move my head to here actually? Because after the next cursor is at this point, so these are also useless. I don't need it anymore. So I can move the head here. Okay, interesting. So think I have reclaimed this much memory. One problem. At this point, it may not be only one cursor. There can be multiple cursor, right? What I will do, I will not delete you, man. I am gentleman. I will not delete you. What I will try to do for you is, I will move your cursor to this point. I will move your cursor to this point actually. So next time you read from here. You don't read from here. But I will tell you when I am giving you the read result, I will put a variable called I'm telling you a lot of things. I am telling you what is the last sequence you read, how much pending messages are there. I will give you one more thing, skipped message, and I will tell you, okay, you have skipped from here to here. This I will give you back, man. I am not so harsh for you. I will not remove you. I will give you the next tail position actually, or next head position. So here I will move the cursor to the head position, and I will reclaim it, and I will tell you. Okay, it's a problem, right? It's a problem. It's a trade-off I'm doing. Now the question: what is the logic behind this trade-off? Hmm. Think up. You are doing a banking transaction, right? You put the money, remove the money, put the money, remove the money, something like that. Okay, and sometimes your queue became full, and you are reading some your accountant or the code which is reading, putting data into the account, how much money is there, how much money is not there. So it's some old cursor, right? If I delete that one and I move to beyond some point, right, you miss this much more transaction. That's going to be catastrophic, right? Catastrophic for financial institute. It cannot be done. The good news is this is an embedded system. This I am doing for an IoT or embedded kind of devices. What will be the input? What will be the input to the queue, or what I am expecting to the input to the queue? Maybe a sensor value, maybe a temperature value, maybe something related to the device type, right? Like something related to the peripheral of the devices, maybe something voltage, something like that, not the transaction. Or think up, the consumer may not need the oldest value. It doesn't require for them because any sensor value should work with the latest value, right? You should not work with the oldest value, right? That's the reason. That's the reason I'm reclaiming the oldest values. Okay, because in my system, in all the design philosophy, what we are doing, it's not for banking transactions, not for any financial institute, but this use case is something where you always, it is, you are expecting a good data or a latest data like a sensor value. You, if you miss 10 sensor value for 10 microsecond, 10 millisecond, but you get the better value, that's fine. Or in your song, when you're listening to some pixel missed, you cannot figure it out also, right? That type of scenario thing. In embedded IoT devices, you always work on the latest data. Okay, that's why they reclaim. So how are we reclaim? Once I'm writing to tell, okay, when the queue is full, the tell will reclaim the oldest, not the oldest. Your data will be like this many memory will be reclaimed, right? The the oldest cursor, and second minimum oldest cursor, second oldest cursor, and I will remove the oldest cursor and put the oldest cursors to the second minimum oldest cursor, second oldest cursor, and I will reclaim this much of memory, right? That's how I'm designing. And this time I'm giving you a new information to the consumer, to the subscriber. I'm saying you, I will give you something called skipped messages, right? So you can have an idea that this many messages are skipped for you. Looks nice. Now my reclaim logic is at its place. Okay, that's fine then. Okay, I want to end this lecture now. I don't want to go through the code. Um, I'm expecting you can go through the code and figure out how the code is written, and so all those things. Okay, we have made one class. That class name is cursor FIFO. So whatever the API at the very beginning we have discussed, if you remember, yeah, this is the class, right? This is the class. So this, sorry, so this class, so this class is, so everything what I will discuss, these are this part of this class, and this class is called cursor FIFO. This class is called cursor FIFO, or shortly we are telling you cfifo. So now in Ninibus, instead of using Nini FIFO, what we've used and derived, developed, implemented, now we're making it obsolete. Not going to use it because it's not going to be helpful for us. Instead I'm doing cursor FIFO, cfifo, okay? So we have an independent repository for cfifo where we have the first stable release, and the same cfifo also we are using here actually, okay, in an Unibus. I will put all the details in the description so you can go and check the cfifo the implementation in that repo. Okay, so now you can think how the cfifo is implemented. Okay, one important thing. I have not implemented cfifo to be thread safe, and I am not going to implement it. The idea is that I'm trying to make an ecosystem of like an STL, like a queue, right? STL queue map. It doesn't guarantee the synchronization. So multiple reader writers doesn't guarantee. So am I. I'm not guaranteeing cfifo going to be. I'm not going to tell you that cfifo is synchronized and guaranteed. No, cfifo doesn't know anything about the threadings. The users need to take care of the synchronization when they're reading or writing. I am just giving you two APIs. I am maintaining a subscriber ID for you. I'm giving a function where you can actually register the subscriber ID. Okay, that's all. So this cfifo is never going to be thread safe unless you do it thread safe when you are using cfifo. Like think of STLs like your queue, your map. No, they don't guarantee, so I don't guarantee. Okay, I don't assume it to be thread safe. But it's really good implementation. You can go through the code. I will put all the things in the description. We have a stable release for this one also, and it can be used. Okay, saying that, just to wrap it around, so we have started with something with what we thought was a small implementation, but slowly we have derived and derived and derived. So it reached something called cfifo. Now, the next thing which you are going to do is multiple consumer or multiple subscriber from different threads to Ninibus. So till the time we have make one single thread, single producer, multiple consumer, but everything is same thread. So now the next problem statement what we are going to solve is the subscribers can have multiple threads. So, and we know cfifo is not guaranteeing formal thread synchronization. So, inside our Ninibus architecture, so if you know Ninibus, how it looks like, in a bus we have a LAN. Okay, we have a LAN. Okay, inside the LAN we have a map. Every LAN object. This is your subscriber ID. This is your LAN ID. Right, and you have a LAN object here. Now the LAN object have a cfifo, right? This is our abstraction. So this person is not guaranteeing synchronization or not doing. So that means something have to be done inside this LAN.cpp or inside the LAN abstraction. So okay, the problem statement is clear. We are not going to do multiple producer, because I told you, like, we have decided that multiple producer have this same lane ID. Okay, multiple producer should use different lane ID, but this lane ID can be shared between multiple subscriber. Okay, this is the next problem statement. This is the next problem statement we are going to do. Okay, we have also released Ninibus v2.0.0. I'm not going through the code of the cfifo, and there are some changes done in v2.0 or 2.0.0. You can go through the GitHub. Very small things are done. Like, we have created some API called subscriber list. Like, because we have to have a subscriber, right? Because same LAN ID was used by multiple subscriber, right? So we have to create that API, right? That's only one thing we have created in the code. Okay, so with this, we have reached to v2.0.0 and completion. So the next thing we are going to do is implementing the next problem statement. Multiple consumer from multiple threads. Okay. For the cfifo side, we have another repo. We have a stable release for cfifo. Not going to touch it. That's a different thing now. It's derived. It's required by it's required by our Ninibus, so we created it and we have moved it aside now. We are not going to use it. We are not going to change it anymore. Okay, saying that, let's have a goodbye. See you next time.